Hi everyone, I am Anson and I work under the guidance of Professor Ranjani at RRI Bangalore. And following is a presentation about the dynamics of granular materials, and this work is still going on and it's in its initial stage. Okay, granular particles. Granular particles are a mixture of discrete solid, macroscopic particles that interact through dissipative frictional force. Also, the constituents composed of the granular material must be large enough such that the temperature fluctuations shouldn't affect them. Thus, the lower limit for the grains in the granular materials must be in the range of micrometer. Hence, there are thermal systems that don't have any long range interaction. Some examples of granular materials are given here like sand, rice, coffee, cornflakes, pebbles, etc. Hence, granular systems have the advantage of conceptually and experimentally very clean or straightforward to realize, and they have the potential to be very controlled. Also, since they are macroscopic, their detection is very easy. So when granular materials are excited, they exhibit a wide range of pattern forming behavior. As such, granular materials under excitation can be thought of as an example of complex system. In experiments, granular particles are realized by 3D printing a large number of particles. So we can use 3D printing to effectively print particles which have an anisotropy inscribed in them so that when excited, they can have a directed motion. These particles can serve as a model system for studying microtubules and actin motors, bacterial colonies to swarms of insects and fish, flocks of birds of large groups of mammals, including humans, which are, if not impossible, difficult to control. So this is the motivation for our experiment. And here is our particle design and experimental setup we have at our institute. So these are the two particles we printed. And this is a 10 mm particle and this is an 8 mm particle. And this is the bottom part of the particle. And this is one leg, which is made up of the same material as the rest of the material, which is essentially plastic. And in this hollow part, we attach another leg made up of PDMS. Hence, we'll be making them as a two-legged particle. Hence, the asymmetry of the particle is in its friction when they are in contact with the surface. And this is the top part, and this is disc shaped. And here is the experimental setup we have for exciting these 3D printed granular particles. So the granular particles are excited using a vibrator surface. When placed in a vibrating plate, granular particles show movements because of the energy gained from the collision with the plates. This here is the electrodynamic shaker, and the top surface vibrates at the desired frequency and amplitude. And this wall setup is housed on two plates, of which the bottom plate is grouted and the upper plate resting on the screws. Using the screws, we can make sure that the top vibrating surface is aligned and the vibration is in fact homogeneous everywhere in the plate. And the surface where the granular particles are excited is an anodized aluminum plate, and the anodization helps get a better contrast for imaging. Also make sure that there is a uniform surface property throughout the plate. And this dynamics of the granular materials are then imaged using a camera which is mounted on the top of it. So these are the results we obtained, and here is the video of the granular particles on the vibrating plate. As you can see, there is in fact some sort of directionality in their motion, and this can be further confirmed by calculating the mean square displacement. And this is the equation we used for calculating the MST. And as you can see here, this is what the MST looked like for a purely diffusive particle. And this is the MST we got for the 10 mm and 8 mm particles. So both 10 mm and 8 mm particles show super diffusive dynamics in the MST plots. So I'm winding up my presentation with this concluding remarks. So the super diffusive dynamics originated from the friction anisotropy of 3D printed particles. When excited, renders them as an effective model system to study active particles. The dynamics and phase aggregation, if any, when binary mixtures are excited, is an interesting topic for future work. We also plan to study how the size ratios of the mixtures of the particles affects the dynamics of the particles. We further plan to study how the stiffness of PDMS legs affect the dynamics and time duration of the collision. So these are the references, and I acknowledge of these people, and thank you for your attention.